In this video, we're going to try to solve this initial value problem here and try to solve for y of s, and then later find the inverse Laplace transform of y of s to find the solution y of t. Now we're going to use the Laplace transform to solve for this second order linear differential equation with constant coefficients and also with piecewise forcing function in our right hand side of our differential equation. Now this function here models a discontinuous function and shows that this has a value of 1 for time t in between 0 to 1 and has a value of 0 for time t is greater than or equal to 1. Now, one of the practical examples of these type of functions can be found in electrical circuits where you model the turning on and turning off of circuits. Now, how I imagine this function in those models, for example, the switching on and switching off in circuits, I can simply think of this as a function that turns on at time t is equal to 0 and turns off at time t is equal to 1. Now, to understand more of this function, let's try to understand the unit step function. And I'm going to show you this here. This is a unit step function denoted as u of c, u sub c of t, or u of t minus c. Now this is equal to 0 for time t is lesser than c and 1 for time t is greater than or equal to c. Now this can be translated in electric circuit model where the switch isn't turned on yet until t is equal to c, meaning prior to c the function is in the off state, and after switching time t is equal to c, the function now is in the on state here. For t is lesser than c, we have 0, and for t is greater than or equal to c, we have 1. Now say we want the switching to happen at t is equal to 0, we'll just change c to 0. That's why we have u of t here and 0 here, 0 here. This means that prior to switching, prior to t is equal to 0, our function is in the off state, and after switching on, the function is in the on state or has a value of 1. Now say also we want the switching to happen at t is equal to 1, we'll change c to 1 here and we'll denote this as u of t minus 1. And notice here that the value of this function is 0 prior to switching, prior to t is equal to 1. And after switching, the value now is 1 and is in the on state here. So we're gonna derive this here out from u of t, and u of t minus 1 are right hand side function of our differential equation, our problem. Notice here that this resulting function here, after we subtracted u of t minus 1 from u of t, is our resulting function in our original differential equation. Remember this. Now, how we got this is simply subtracting u of t minus u of t minus 1. For time t is lesser than 0, we have u of t here as 0 and u of t minus 1 here as 0. So 0 minus 0 is 0. And for time t in between 0 to 1, we have u of t here as 1. And we have here u of t minus 1 is 0 since u of t minus 1 is still in the off state here. So 1 minus 0 is just 1. That's why we have 1 here. And at t is greater than or equal to 1, we have our u of t is 1 And our u of t minus 1 is also 1. So meaning 1 minus 1 is 0. Now the resulting function is a square wave. Now we can read this as in between 0 to 1, we have our value 1, and for t is greater than or equal to 1, we have 0 here. That's why this is our new function. So meaning we can say, let's go back to here. This is our function, and this can be written in this form here. This here. This is our function, and this can be written as this 1 minus u of t minus 1. Now, if you're confused why u of t is just 1, simply imagine that our u of t has always a value of 1 for time t is greater than or equal to 0, since we're dealing only with positive time, and the domain of our t is from 0 to infinity. So meaning our u of t is always 1, since we're neglecting for this here for t is lesser than 0. So this function here can be denoted as this one, 1 minus u of t minus 1. The purpose of this is to easily find the Laplace transform. So we're gonna go back to our original problem. We have this. This can be rewritten as this. To easily remember this, you can write 1 here and then subtract right away u of t minus u of t minus 1 here. This just cancels because this is 0. Then we have this. Taking the Laplace transform of both sides of the equation and using this formulas here, we have these formulas, and let's plug that in here after taking the Laplace transform. We have this. Substituting this initial values, zeros, and this cancels out because this is just 0, and we're left with this one. And also the Laplace transform of this right hand side here is because of this. Wait. Because of this. This is just the Laplace transform of any unit step function. If your c is, for example, 1 here, you just change 1 here. If your c here is 2, you change 2 here. This is just the Laplace transform of the unit step function. Let's go back to our problem. And so that's why we have here u of t minus 1, the Laplace transform is e to the negative s over s. And we can find the expression for our y of s here. This is our y of s, and let's take the inverse Laplace transform of this y of s here, but let's first decompose this expression here into partial fraction and find the unknowns a, b, and c. This here, you can easily find these unknowns here by setting values of s that makes these terms, the other two terms, to be cancelled out. For example, we set s equal to 0 so that we can cancel the terms containing b and c. so that we'll find A here easily. And we've found A. And the same cases for B and C. We just set S is equal to -2, and this term here containing A and C cancels out. And B already found that our B is this. Same with C, setting S is equal to 8. So, and then the term containing A and B cancels out, and C is equal to this. And we now already express this into partial fraction, and we can now find the inverse Laplace of this y of s here, given our formula. And we just distributed this so that we can easily take the inverse Laplace of y of s. Then we take the inverse Laplace individually. This is just a formula from this here. And our y of t is now this. And we can check that our answer is correct from here. And I think that's all.